Good morning, everyone, and welcome back to the physics session. So, in this session, we are going to study the chapter 3 from class 12, which is the kinetic theory of gases. So, in the kinetic theory of the gases, basically, we are going to study the different laws associated with the gas or the motion of the gas. So, in that, we will study the Boyle's law, Charles' law, Gay-Lussac's law, then equation for mean free path, then equation for RMS speed of the gas molecule, then energy equation, specific heat capacity, then the laws related with the radiation. So we have the coefficient of emission or the emissivity, Kirchhoff's law, Wien's displacement law, and Stefan's Boltzmann law. Okay, so we will study this in detail one by one. So the first equation, which shows the relation between volume and the pressure. So this equation is given by the Boyle's law. So Boyle's law equation is volume is inversely proportional to the pressure and condition is at the constant temperature. Second equation, it is the Charles law. So Charles law gives the equation volume of the gas is a proportional to the temperature and at the constant pressure. And the third equation is a Gay-Lussac's law. So Gay-Lussac's law gives the equation pressure is a proportional, that is a directly proportional to the temperature at the constant volume. So in the Boyle's law, volume is inversely proportional to the pressure at constant temperature. Charles' law, volume is proportional to the temperature at the constant pressure. And the Gay-Lussac's law, pressure is directly proportional to the temperature at the constant volume. Okay. If we combine all these three laws into a single equation, then it gives the ideal gas equation. So we have the ideal gas equation by combining all above three laws. So pressure into volume, this product is a directly proportional to the temperature. Okay. And this is for fixed mass of the gas. So from this equation, if you have two different conditions for pressure and volume, so P1 V1 upon T1 is equal to P2 V2 upon T2. So for a particular gas, if the pressure is increasing from P1 to P2 and volume changes from V1 to V2, then we can write this P1 V1 upon T1 is equal to P2 V2 upon T2. Okay. From this same equation, which is a PV is proportional to the temperature, we can write the equation by introducing a constant, which is the gas constant R. PV is equal to N RT. So product of pressure and the volume is equal to N RT. So N is number of mole. R is the gas constant. And the gas constant, its value is 8.314. This is joule per mole Kelvin. Now the number of mole N we can determine by using this formula. N is equal to mass of the gas divided by the molar mass of the gas. So mass of the gas we can represent as a capital M, and the molar mass, which is the m naught. This equation we can also write in terms of the Avogadro's number. So total number of molecules of the gas divided by the Avogadro's number, which is the Na, this is equal to, this capital N is nothing but number of molecules in the gas divided by number of molecules in 1 mole of gas. So you should remember this formula. So the first formula for number of mole, which is this small n, is mass of the gas, that is the capital M, divided by the molar mass, which is the m naught. Or second equation is number of molecules in the gas, which is the capital N, divided by number of molecules in 1 mole of gas. This number of molecule in 1 mole of gas, this value is a constant. So Na, this is the constant value. Okay, next concept for the gas, it is the mean free path. So what is meaning of mean free path? Suppose we have one container or a closed vessel, and there is a gas at a particular pressure. Let us take this pressure of the gas is P. Then the mean free path of gas means these are the molecules of the gas, which is shown by dots. So average distance traveled by a molecule between two successive collision. Okay. So each molecule have the possibility it may collide with the adjacent molecule during its free motion. Okay. So average distance traveled by a particular molecule before colliding with the other molecule. Okay. So this average distance, so it is the average distance traveled by the molecule between two successive collision. So mean free path, it is represented as a lambda. So lambda is inversely proportional to the density. So here density is equal to number of molecules per unit volume. Also this lambda, which is the mean free path, is inversely proportional to the square of the diameter. So here capital T is the diameter of the molecule. So by combining all these two equations, we have the final equation for lambda, which is the mean free path. So this is equal to 1 upon square root 2 into pi d square into n upon v. So this n upon v is nothing but the density. Basic equation we have is PV is equal to nRT, or this equation can be written as a PV is equal to n Kb into T. So n is number of molecules, and this Kb, this is the Boltzmann constant, and its value is 1.38 into 10 to the power minus 23 joule per Kelvin. Okay, so this is the equation for mean free path. Lambda is equal to 1 upon square root 2 pi d square into n upon v, or density. Okay, now next equation we have about pressure of the ideal gas. So average pressure inside a container. So suppose we have one container like this, and there is a gas pressurized inside this container. Then this pressure P, it is given by the equation P is equal to 1 by 3 n upon volume. So n is the number of molecules into m, which is the mass, and v square average, which is the average velocity. Next we have the root mean square speed, which is the RMS speed of the gas molecule. So this is VRMS, or sometimes it is represented as a C. So its equation is VRMS, which is the root mean square speed of the gas molecule. It is square root 3RT divided by m naught. Okay. So m naught is nothing but the molar mass, and it is given by m naught is equal to, its equation is Na, which is the Avogadro's number, into m. So this equation we can also write, this is equal to 3p upon rho. So VRMS first equation is square root 3RT upon m naught, or 3p upon rho. Okay. So here basically we are replacing PV by nRT. Okay. Then next equation we have about energy of gas. So energy in the gas, it is calculated from the basic equation of the pressure, which is equal to 1 by 3 N upon V m V square average. So if I adjust this term, if I take volume on the left side, so P into V is equal to 1 by 3 N m V square average. Now we will write this equation in terms of the kinetic energy. So we have the velocity square term, we have the mass of the gas. So just write here 1 by 2. So this is 1 by 2 mass V square average, and just adjust this 2, so it will become 2 by 3 into N. Okay. Now this term is the kinetic energy. So we can write this 2 by 3 N into kinetic energy. This is equal to PV. Okay. Now in the gas, we just have the kinetic energy associated with the gas molecule. We don't consider the potential energy. Okay. So total energy in the gas, which is the capital E, is the kinetic energy because of all the molecules. Okay. So capital N into kinetic energy associated with the single molecule. So this term N into kinetic energy, we can directly write as a total energy E. So this is equal to 2 by 3, this capital N into total energy is E. Okay. So this is equal to PV. Sorry, this is not N. This N into kinetic energy is nothing but the total energy. And from this we get the equation total energy associated with the gas. This is equal to 3 by 2 into P into V. So this is the basic equation for the energy in the gas. And we have second equation for PV. One equation is nRT. And also we can write PV is equal to, this is NKB, which is the Boltzmann constant, number of molecules, into T. Okay. So from this we get E is equal to 3 by 2. We can just replace PV. So this is equal to NKB into T, and we can write energy, total energy divided by number of molecules is equal to 3 by 2 into Boltzmann constant into temperature. Okay. So we have these two equations for the energy. One is E is equal to 3 by 2 PV, and second equation is E by capital N, which is the number of molecules, is equal to 3 by 2 Kb into T. Next we have the specific heat capacity. So in the specific heat, we have two different specific heat. One is a Cp and second is the Cv. So Cp, it is the specific heat capacity at constant pressure, and Cv is a specific heat capacity at constant volume. So the relation between the specific heat capacity at constant pressure, which is the Cp, and Cv, it is given by the relation which is called as a Mayer's relation. So Mayer's relation is the difference of which is a Cp minus Cv, this is equal to the gas constant, which is the R. So this relation is derived from the basic equation for the heat. So for constant volume, so if we are keeping the volume constant, so suppose we have in arrangement, this is a cylinder and this is the piston, and this is the gas inside the cylinder, and suppose we add the heat, and if this volume is constant, we are not moving the piston, so volume is constant, then heat added will only utilize to increase the internal energy. Okay, so at the constant volume, the amount of heat supplied, which is the dq, is only used to increase the internal energy, so it becomes de, and this is equal to de. We can write this as a Cv, which is the heat capacity at the constant volume, into change in the temperature, so Cv into dt. At the constant pressure, so if you want pressure to remain constant and if we supply the heat, then this piston will be moved in the upward direction, so its volume will change. So heat supplied dq, it is partially utilized to increase the internal energy, so it is a de, and remaining heat is utilized to do the work, so it is the dw. So we have the equation for d, which is a Cv into dt, and this dw, which is the increase in the work, this is equal to, so this is dw. So this total heat supplied, this is equal to Cp into dt. Okay, now from this equation we can write Cp minus Cv into dt, this is equal to, so dw, this is the work done, this is nothing but pressure into change in volume. So when we supply the heat, and if you want pressure to remain constant, we have to increase the volume, and therefore piston will move in the upward direction. Okay, so there will be change in the volume dv, and pressure is a constant, so this is equal to dw, which is nothing but p into dv. Okay, so we have the equation Cp minus Cv into dt, this is equal to p into v, and this equation it is written as Cp minus Cv, this is equal to p dv upon dt, and this is equal to gas constant, which is the R. Now this heat supplied Q, it is measured in the calorie, and the work done is measured in a joule. Okay, so there is one conversion, which is Cp minus Cv, this is equal to R upon J, and this constant J, this is called as a mechanical equivalent of heat. Okay, next we have the relation between Cp and Cv. Basically, it is the ratio, which is equal to gamma. And this gamma has a particular value for different gases. So first we have the monoatomic gas. So for the monoatomic gas, the ratio Cp by Cv, its value is 5 by 3. Second, we have the diatomic gases. So in the diatomic gases like O2, H2, then HCl or the N2. Okay, for such gases, the ratio gamma, which is a Cp by Cv, this is equal to 7 by 5. This is for rigid vibrating molecule. And gamma is equal to Cp by Cv, this is equal to 9 by 7. This is for non-rigid molecule. Third, we have the polyatomic gases. So in the polyatomic gases, the constant gamma, so this is written as 4 plus F divided by 3 plus F. Okay, and where this F is nothing but the degree of freedom. So for a particular polyatomic gas, is the degree of freedom is given, then by using this formula, you can determine the ratio Cp by Cv. Okay. So this is about the specific heat capacity of the gas. The next concept is about the radiation. So radiation is nothing but continuous emission of energy from the surface of the body because of its thermal energy. Okay. So it is the continuous emission. Radiation is the fastest mode of heat transfer, and it doesn't require any medium. So suppose the total heat which is falling on one object is a Q. Partial heat is transmitted, which is the QT. Some amount of heat is absorbed, which is used to increase the internal energy, and the remaining heat will be transmitted, will be radiated. So it is a QR. Okay. So total heat supplied Q is equal to the amount of heat absorbed, amount of heat radiated, and amount of heat transmitted. Okay. And from this, we have the relation for coefficient of absorption plus coefficient of radiation plus coefficient of transmission. This is equal to 1. So A is nothing but coefficient of absorption. This is given by amount of heat absorbed divided by total amount of heat supplied. Coefficient of radiation R, this is equal to total heat radiated divided by total heat supplied, and the coefficient of transmission Tr, this is equal to total heat transmitted through the object divided by total heat supplied. And from this we have the relation A plus R plus Tr is equal to 1. Now from this relation, which is A plus R plus TR is equal to 1, we have some special substances. So in that first we have dithermanous substance. So in the dithermanous substance, the transmission coefficient is not equal to 0. So it is not a good absorber, or not a good reflector. So some amount of heat will be absorbed, some amount of heat will be reflected, and some will be transmitted. Okay. So in this we have the substances like a quartz crystal, then sodium chloride, normal salt, then hydrogen, and the glass. Okay, so these are some examples of the diathermanous substance. Second is a thermanous substance. So for this substance, we have transmission coefficient is 0. So no heat is transmitted through the object, and therefore we have the relation from this basic equation A plus R, that is the coefficient of absorption plus radiation, it is equal to 1. This is for a thermanous substance. So this substance, it is opaque to the radiation. It means that radiation cannot pass through the substance, and therefore it is opaque. And second example is wood, then iron, copper. Third substance is a good reflector. So good reflector, it means its transmission coefficient must be 0 and absorption must be 0. Okay. So the radiation falling on the object or the surface must be completely reflected. So coefficient of absorption, it must be equal to 1. And the last we have the perfectly black body substance. So perfectly black body means if all the radiation falling or the incident on the surface will be absorbed, then it is referred as a perfectly black body. So absorption coefficient for the black body is equal to 1. It means that transmission coefficient is 0 and the radiation is 0. So in case of perfectly black body, it absorbs entire radiation. Which is incident on it. So if any substance is a good absorber, they are good emitter also. So poor absorber or poor emitter. The poor absorber surface must be a good reflector, and vice versa. And good reflector is a poor emitter. Okay, so remember all these points. Next, we have the equation for emissive power. So emissive power or the radiant power, this is also called as radiant power. So R is equal to Q divided by AT. So here Q is the heat radiated, T is the time, and A is the surface area of the body. And unit for this emissive power, it is joule per meter square second, or this is watt per meter square. And the dimension is, this is the L0, M1, and T minus 3. Next, we have the equation for coefficient of emission. Or this is called as the emissivity. So coefficient of emission, E, this is equal to the emissive power of a given surface, R, divided by emissive power of a perfectly black body. So this is emissive power of given surface or any surface divided by the emissive power of perfectly black body. So for a black body, the coefficient of emission or emissivity, this is equal to 1. And for a good reflector, which is a perfect reflector, the emissivity, sorry, coefficient of emission or the emissivity, this value E is equal to 0. And for any other surface which is not a perfectly black body or a perfect reflector, value of E, it lies between 0 and 1. Okay, 0 means it is a good reflector, and E is equal to 1 means it is the perfectly black body. Next, we have the Kirchhoff's law. So Kirchhoff's law, R upon A, this is equal to emissive power divided by coefficient of absorption. So this ratio is equal to emissive power of perfectly black body. So ratio emissive power of a given surface divided by the coefficient of absorption, it is equal to RB, emissive power of black body. Okay. Next, we have the Wien's displacement law. So Wien's displacement law, the wavelength for which emissive power of perfectly black body is a maximum is inversely proportional to the temperature. Okay. So lambda is inversely proportional, or lambda max, to the temperature. Okay. And lambda max is equal to B upon T. Or we have lambda max into T is equal to B. So this is called as a Wien's displacement law. And here the constant B, this is called as a Wien's constant, and its value is 2.897 10 to the power minus 3 meter Kelvin. Okay. So the equation for Wien's law is lambda max into T is equal to B, and the lambda max is the wavelength for which emissive power of a black body is a maximum. And last we have the Stephens-Boltzmann law. So Stephens-Boltzmann law, it gives a relation: the power radiated per unit area of perfectly black body, which is the R, is directly proportional to the fourth power of absolute temperature. So power radiated or energy radiated, so R, it is the energy radiated per unit area of perfectly black body, and T is the absolute temperature. So we can write the same relation by using the constant R is equal to sigma T raised to fourth. So sigma is called as a Stefan-Boltzmann constant. So sigma is equal to 5.67 10 to the power minus 8 joule per meter square second Kelvin raised to fourth. Okay. And this R, this is equal to, we already seen, Q upon AT. And therefore Q upon AT is equal to sigma T raised to fourth. For ordinary body, this relation is for perfectly black body. So for ordinary body or ordinary surface, energy radiated R, this is equal to emissive power or the emissivity of the surface E into sigma T raised to fourth. So this is the energy radiated for an ordinary surface, which is not the perfectly black. So E is the emissive power, so emissivity, sigma is the constant, and T raised to fourth, which is the absolute temperature. So suppose we have one body, and this is the perfectly black body, and it is having the absolute temperature, let us take T. Okay. And it is kept in the environment, and this environment has a temperature which is a T naught, which is a less than T. Okay. Then the energy radiated or the loss of energy, so this is the energy radiated, So this loss of energy, this is given by sigma T raised to fourth. So T is the temperature of that body minus T naught raised to fourth, which is the temperature of the environment. Okay. Now for the body, for any other body, so this is for perfectly black body, for ordinary body, just multiply this equation by the emissivity. Okay. So loss of energy, this is equal to E sigma T raised to fourth minus T0 raised to fourth. Okay. And suppose the surrounding temperature is greater than the temperature of the body. So if T is less than T naught, then the loss of energy or the gain of energy, this is not the loss, gain of energy, this is equal to emissivity into sigma T naught raised to fourth minus T raised to fourth. Okay. Okay. Now this is all theoretical part. Now we will solve the MCQs. Okay. Refer the first question. At 0 degree Kelvin, which of the following property of the gas will be zero? Density, potential energy, kinetic energy, and the vibrational energy. Okay. As we know, gas contains the number of molecules which are continuously moving. So at the absolute zero, it means minus 273 Kelvin. At this temperature, the molecular velocity, it will be zero, and therefore its a kinetic energy will be zero. Okay. So always remember, at the absolute zero temperature, the gas will not have any kinetic energy. Okay. So correct option is the option C, kinetic energy is zero. So kinetic energy, it is zero at absolute zero temperature. Refer the second question. The equation for an ideal gas is PV is equal to RT, where V represent the volume of 1 gram of gas, second any mass of the gas, 1 mole of gas, and 1 liter of gas. Okay. So for the ideal gas, we have the equation PV is equal to N RT. Okay. So in this equation, N stands for number of moles. So as the given equation is PV is equal to RT, it means N must be 1. Okay. And 1, it is not the gram of gas. So it is 1 mole of gas. Okay. So correct option is option C. Refer the third question. The change in the temperature of the body is 50 degrees Celsius. The change on Kelvin scale is, okay. So we have the relation for absolute temperature is equal to temperature in degrees Celsius. I will take this as a T naught plus 273 Kelvin. So this is the absolute temperature. Okay. So if this temperature rises by 50 degree, So absolute temperature will also rise by the same amount, 50 degree. Okay. So the correct option is the change in the temperature of the body is 50 degrees Celsius. Change in the Kelvin scale. Kelvin scale means change in the absolute temperature. It will be same, which is the 50 Kelvin. Sorry. Yes, it is 50 Kelvin. Okay. So correct option is option A. Refer the fourth question. The product of pressure and the volume of an ideal gas is first constant, approximately equal to the universal gas constant, inversely proportional to its temperature, or directly proportional to its temperature. Okay. So this is based on the Gay-Lussac's law. Sorry, ideal gas equation, which is a PV. So PV upon T, this value is constant. So PV is directly proportional to the temperature. So product of pressure and volume. So this product is proportional to its temperature. Okay. So correct option is option D. Okay. Refer the fifth question. At a given volume and the temperature, the pressure of the gas first is varies inversely as its mass. Second, varies inversely as the square root of its mass, varies linearly as its mass, and it is independent of its mass. Okay. So at a given volume and temperature, pressure of the gas. So we have the equation PV is equal to N RT. Okay. And N, we have the equation mass of the gas, which is the M, upon the molar mass M naught. Okay. So this is the mass of the gas divided by molar mass. So we can write this PV is equal to M upon M naught into R into T. Okay. So pressure is a directly proportional to the mass. So correct option is option C. So varies linearly as its mass. Refer the sixth question. The molar gas constant is the same for all the gases because at the same temperature and the pressure, equal volume of gas have the same density, kinetic energy, ratio of heat capacities, or number of molecules. Okay. So correct option is option D. So Na, this value is nothing but number of molecules divided by 1 mole of gas. So this is the Avogadro's number, and this value is a constant. So Avogadro's number means the total number of molecules per unit mole of the gas, and this value is 6.023 into 10 to the power 23. Okay. And therefore molar gas constant is the same for all the gases because at the same temperature and pressure, equal volume of gases have the same number of molecules. Okay. Refer the next question. An ideal gas is that which can be solidified, can be liquefied, cannot be liquefied, and not be solidified. Okay. So ideal gas means for the ideal gas we cannot liquefy it. So correct option is a C. The ideal gas in that is that which cannot be liquefied. Okay, refer the question 8. The expression for mean free path, which is the lambda of molecule, is given by the equation. So equation for mean free path is lambda is equal to 1 upon square root 2 pi d square n number of molecules divided by the total volume. Okay, so this n upon v, it is represented as a nv. Okay, so correct option is square root 2 pi d square nv, and this is a 1 upon, so correct option is option C. So remember this basic formula for lambda, which is the mean free path. Okay, refer the next question. The mean free path of the molecules of the gas, if radius is r, is inversely proportional to. Okay, so we have to find out the relation between lambda and the radius of the molecule. Okay, so the standard equation for lambda is 1 upon square root 2 d square, or this is a pi d square n upon v. Okay, just replace this d, so d will be 2r square, so it will become 4r square. Okay, so lambda is a proportional to 1 upon r square. Okay, so it is inversely proportional to the radius square. So option correct is B. For the next question. At a constant volume, temperature is increased, then collision on the wall will be less. Number of collisions per unit time will increase. Collision will be in a straight line, or collision will not change. Okay, so as we increase, so suppose the volume is constant. Okay, and if we supply the heat, so it will increase the temperature. So as the temperature increases, the kinetic energy of the molecule will increase. Okay, and therefore they will collide with the other molecule, and therefore number of collisions per unit time will increase. So correct option is B, if you increase the temperature keeping the volume constant. Refer the next problem. The density of air at a pressure of 10 to the power 5 Newton per meter square is 1.2 kg per meter cube. So this is the pressure given for the air. Under this condition, the RMS velocity of the air molecule in meter per second is. Okay, so what is given? The density of air is given, which is the rho, and this density is 1.2. Then pressure is given P, which is equal to 10 raised to 5 Newton per meter square, and we have to find out the RMS speed, which is the VRMS or C. Okay, so we have seen the standard relation for the RMS speed. VRMS is equal to, this is equal to square root 3p upon rho. Okay, or we have the second equation, which is equal to 3 into gas constant into temperature divided by the molar mass, which is the m naught. Okay, so here pressure is given and the density is given, so it is square root 3 into p, so p is 10 raised to 5 divided by density is 1.2. Okay, so we can write this equation as, so 3 divided by 12, so 12 means 1.2 means 12 into 10 to the power minus 1 into 10 to the power 5. Okay, so 3 4, it is 1 by 4, so square root 1 by 4 into, take minus 1 in the numerator, so it is 10 to the power 6. 1 by 4 square root is 1 by 2 into 10 raised to 3. Okay, so 1 by 2, it means 0.5, 10 raised to 3, and this is equal to 500. So 500 meter per second. This is the RMS speed. Okay, so correct option is option A. So for the RMS speed, if the pressure and the density is given, then we can use the formula VRMS is equal to square root 3p upon rho. Refer the next problem. The RMS velocity of the hydrogen gas at normal temperature and pressure is V meter per second. The gas is heated at the constant volume till the pressure becomes 4 times. The final RMS velocity is, so we have the VRMS, which is equal to V. This is equal to square root 3p upon rho. Okay. New RMS speed V dash is equal to 3. Pressure is 4 times, so 4p divided by rho. This is equal to 2 in bracket 3p upon rho. So this is equal to 2 into V. So new RMS speed V dash, this is equal to 2 times the V. So option is option A. Refer the next question. 4 molecules of speed 2 km per second, 3 km per second, 4 and 5. The RMS speed of these molecules in kilometer per second is. So for the RMS speed, if the speed of individual molecule is given, then we can use this formula C or V RMS. This is equal to square root C1 square plus C2 square, C3 square, C4 square divided by number of molecules, that is 4. Okay, so this is equal to square root, this is 2 square, 3 square, 4 square plus 5 square upon 4. So 2 square is 4, this is 9, 16 and 25. So if you add all these values, you will get the answer as a 54 divided by 4. Okay, so square root 54 upon 2. So this is the RMS speed. So option given is the option B, which is square root 54 divided by 2. Okay, So if the individual speed of gas molecule is given, and then we can use this formula. Refer the next problem. A gas is compressed isothermally, that means at the constant temperature. The RMS velocity of its molecule, whether it will increase, decrease, first increases, then decreases, remains the same. Okay. So if the gas is compressed isothermally, then that is means at the without changing the temperature. Okay. Then its the RMS velocity, it will remain same. So velocity will change, that is RMS velocity will change if there is increase or decrease in the temperature. Okay. So isothermally, gas is compressed isothermally, then velocity will remain same. Refer the next problem. The mean kinetic energy of 1 gram mole of a perfect gas at absolute temperature T. So the correct option is D. We have the equation for energy as E is equal to, or E upon N, this is equal to 3 by 2 kb into T. So total or the average energy for a gas, this is equal to 3 by 2 N kb into T. Okay. And this N kb is nothing but N RT. Okay. So we have already seen N kb, product of Boltzmann constant and the number of molecules. This is equal to number of moles into gas constant. Okay. So for a 1 mole or 1 gram mole, it means N value is 1. So energy is equal to 3 by 2 RT. Okay. So option given, which is the option D, 3 by 2 RT. And this E is nothing but average or mean kinetic energy. Refer the next problem. The kinetic energy of 1 gram molecule of a gas at normal temperature and pressure is, so average kinetic energy. So we have just seen the equation E is equal to 3 by 2 RT. It means that E is directly proportional to the temperature. So average kinetic energy is directly proportional to the absolute temperature. So E is proportional to T. So if I write this, E1 is proportional to T1 and E2 is proportional to the temperature T2. Okay. So if I take the ratio E2 upon E1, so we can cancel out the proportionality. So we can write E2 by E1 is equal to T2 upon T1. So now refer what is given in the problem. So average kinetic energy of the gas molecule at 27 degrees Celsius is 6.21 10 to the power minus 21 joule. The average kinetic energy at 227 degrees Celsius will be, so we have the relation E proportional to T. So we can write E2 upon E1 is equal to T2 upon T1. Okay. So E1 is given. So E1 is equal to 6.21 10 to the power minus 21 joule. We want to find out the E2. So average kinetic energy of the gas molecule at 27 degrees Celsius. So T1 is 27. It means 27 plus 273. This is equal to 300 Kelvin. E2, the temperature is T2, which is equal to 227 degrees Celsius plus 273. So this is equal to 500 Kelvin. Okay. So E2 upon E1, which is a 6.21 10 to the power minus 21. This is equal to T2 is a 500 divided by 300. Okay. So from this you will get E2 is equal to, so cancel out this. So this will be 5 by 3 into 6.21 10 to the power minus 21. So if you simplify this, you will get the answer E2 is equal to 10.3 into 10 to the power minus 21. Okay. So the option given, which is close to this value, is option B. Okay. So average kinetic energy at 227 degrees Celsius will be 10.3 10 to the power minus 21. Okay. So basic relation is the average energy is proportional to the temperature. So you can take the ratio E2 by E1, which is equal to T2 upon T1. Refer the next question. If number of molecules of H2 are double that of the O2, then ratio of kinetic energy of hydrogen and that of the oxygen at 300 Kelvin is, okay. So this ratio will be 1:1. So kinetic energy of hydrogen, it is same as that of the kinetic energy of the oxygen when temperature is same. So at the constant or same temperature. So at the same temperature, different gases will have the same kinetic energy. So the ratio of kinetic energy of hydrogen and oxygen at 300 Kelvin is 1:1. Okay, refer the next problem. A cylinder of capacity 20 liter is filled with the hydrogen gas. Total average kinetic energy of translatory motion of its molecule is 1.5 10 to the power 5. The pressure of hydrogen in the cylinder is, okay. So here the volume is given. So cylinder has capacity 20 liter. So V is 20 liter. So 20 liter means 20 into 10 to the power minus 3 meter cube. Then total kinetic energy is given. So E is given. This is equal to 1.5 10 to the power 5 joule. And question is we have to find out the pressure of the hydrogen in the cylinder. So use the relation for average kinetic energy. E is equal to, this is 3 by 2 PV. So E value is 1.5 10 to the power 5. This is equal to 3 by 2 into pressure into volume is 20 10 to the power minus 3. So we can write pressure is equal to, so take this 2 on the left side. So this is 3, or you can cancel out this 2. This is 10. This will be 30. So 1.5, this is divided by 30. this 10 to the power minus 3 into 10. So this will be 10 to the power minus 2. Okay. So you can write this 15 as 1.5 as 15, 10 to the power minus 1. So this is 10 to the power 4 divided by 30 and 10 to the power minus 2. So this is 10 to the power 2. So this is 1 by 2, 10 raised to 6. So this is 0.5, 10 raised to 6, which is equal to this is 3. So this will be 1.5 by 3. So this is 2. This will be remain 5. So this is 7. So 0.57, or this is 5 into 10 to the power 6. Okay, so correct option is option D, 5 into 10 to the power 6. Okay, refer the next problem. If for hydrogen gas Cp minus Cv is equal to A, and for oxygen Cp minus Cv is B, where Cp and Cv are specific heat at constant pressure and volume per unit mass, then we have to find out the relation between A and B. Okay, so we have the equation Cp by Cv, which is R upon M. Okay, so we can write Cp minus Cv is equal to, for hydrogen gas we have M is 2, which is the molecular weight, and for oxygen Cp minus Cv, which is R upon 32. Okay, so this is for hydrogen and this is for oxygen. Okay, now for hydrogen Cp minus Cv, this value is given as A, and for oxygen it is B. So A is equal to R by 2 and B is equal to R by 32. Okay, so if you take the ratio A upon B, then this is R by 2 upon R by 32. So this is 32 by 2. So this is 16 by 1. Okay, so A is equal to 16 times B. So correct option is option B. So remember this equation Cp minus Cv. Okay, so this is given in terms of the molecular weight R upon M. Okay, refer the next problem. The molar specific heat of oxygen at a constant pressure is 7.03 and R is 8.31. The amount of heat taken by 5 mole of oxygen when heated at a constant volume from 10 degrees Celsius to 20 degrees Celsius. Okay, so given value is Cp, which is 7.03. Then R is given, which is 8.31. So Cp is given as a calorie per mole and R is given as a joule per mole. So convert this joule per mole in terms of calorie per mole. So divide this 8.31 by 4.2. So this will be in calorie per mole degree Celsius. Okay. So this product, this ratio 8.3 divided by 4.2, we can approximately write as a 2. This is calorie per mole degree Celsius. Okay. Now next, number of moles are given, which is of 5 moles. So we have to find out amount of heat taken by 5 moles of oxygen. Okay, when it is heated from 10 degree to 20 degree. So initial temperature T1. So 10 degree means 10 plus 20, 273. So it is a 283 Kelvin. And to T2, it is a 20. So 20 plus 283. So it is a 293. This is the absolute temperature. Okay. Now we have the equation Cp minus Cv. This is equal to R. So Cp is given 7.03 minus Cv. This is equal to R. So R is 2. So Cv is equal to 5.03. So this is calorie per mole degree Celsius. And from this Q, this is equal to N Cv delta T. Okay. So this is the amount of heat taken. So N is number of moles. So 5. Cv, this is 5.03 into delta T. So delta T is 283, 293 minus 283. So delta T is 10. So if you find out this product, so this is 5 into 50.3. So this is approximately 250 calorie. Okay, so correct option is option C. So you should know this formula. First is conversion of R, which is in joule per mole, into calorie per mole. So we have to divide this by 4.2. Okay. Then next is this formula Cp minus Cv is equal to R. And last is the heat. So Q is equal to N number of moles into Cv into delta T. Okay. So we can use this relation only for constant volume. For the next problem. The emissive power, so this is on the radiation, emissive power of a sphere having the area 0.02 meter square. This emissive power is 0.5. What is the amount of heat radiated by the spherical surface in 20 seconds? Okay. So heat radiated, we can determine by the formula of emissive power. So emissive power is equal to heat radiated divided by time into surface area. Okay. So this value is given 0.5 kilocalorie per second per meter square. This is equal to heat radiated divided by time is 20 seconds into surface area is 0.02 meter square. Okay. So Q is equal to, this is 0.5. So 5 10 to the power minus 1 into 20 into 2 10 to the power minus 2. Okay. So this is 5 into 2, 100 into 2, 200. So this is 200 10 to the power minus 3. So this is equal to 2, 0.2 calorie, or unit is kilocalorie. So correct option is 0.2 kilocalorie. That is option A. So you should remember this basic equation. Emissive power is equal to heat radiated divided by time into surface area. Okay, refer the next problem. A body radiates 5 watt energy at temperature of 400 Kelvin. If the temperature is increased to 1200 Kelvin, then it will radiate the energy. Okay. So energy radiated, R, is directly proportional to the fourth power of the temperature. So this is based on the Stefan's Boltzmann law. So from this we can write R1 is proportional to T raised to fourth and R2 is proportional to T raised to fourth. Okay, so this is T1 and this is T2. So you can take the ratio R2 by R1. This is equal to T2 raised to fourth divided by T1 raised to fourth. Okay, so we have to find out the heat radiated at a 1200 Kelvin and initial heat radiated is given. So R2 R1 is equal to 5 watt. T2 is 1200 divided by T1 is 400. So from this R2 is equal to 5 into, so we can cancel out this 3 raised to fourth. So 5 into 81 and this is equal to 405 watt. Okay, so heat radiated at the temperature of 1200 Kelvin. So answer is option C, 405. So equation to be used is R proportional to fourth power of the temperature, which is the Stephens-Boltzmann law, or R is equal to sigma T raised to fourth. And this is the last question in today's session. A sphere is at the temperature of 600 Kelvin. Its rate of heat loss is R1, which is the energy radiated, in an external environment of 200 Kelvin. Okay, so surrounding temperature is 200 Kelvin and the sphere temperature is 600. Its temperature falls to 400 Kelvin. Then what is the heat loss, rate of heat loss? So when a body is kept in an environment, so body temperature is T, and suppose the environment is having the temperature T naught. Okay, so heat radiated we can give by this relation. R is proportional to T raised to fourth minus T0 raised to fourth. Okay, so here we have two conditions. So first is we can write R1 is proportional to T1 raised to fourth minus T0 raised to fourth, and R2 is proportional to T2 raised to fourth minus T0 raised to fourth. Here T1 and T2, these are body temperature. The first body temperature is T1, which is a 600 Kelvin. Second body temperature T2, this is equal to 400 Kelvin. Okay, and the environment temperature is same. So T0 is equal to 200 Kelvin. Now here you can take the ratio of R2 by R1. So this is equal to T2 raised to fourth minus T0 raised to fourth divided by T1 raised to fourth minus T0 raised to fourth. So T2, this value is 400 minus 200 raised to fourth, and T1 value is 600. Now to simplify this, we can write this 400 as a 4 into 10 square. So 4 minus 200 will be 2 into 10 square. 600 is 6 into 10 square. So 10 square raised to fourth, it will be 8. So we can write this 4 raised to fourth minus 2 raised to fourth into bracket into 10 to the power 8. Okay, so you can take 10 to the power 8 common. Similarly, 6 raised to fourth minus 2 raised to fourth into 10 to the power 8. Okay, so we can cancel out this value, and then we can write this 4 raised to fourth, it is a 256 minus this is 16, which is a 2 raised to fourth, 6 raised to fourth, so it is 36 into 36. So if you multiply this, you will get the answer 1296. So this is 1296 minus 16. Okay. So try to simplify this. You will get the final answer as 3 by 16. So R2 upon R1, this value is equal to 3 by 16. So it means that R2 is equal to 3 by 16 into R1. So correct option is option A. Okay. So today we will stop here.